of a mathematical nature. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just ask you to guide our steps today. Help us to understand a little bit more about Laplace transforms and how to use them. In your name I pray, Lord Jesus. Amen. If you were not here last time and did not get this sheet, I'd be happy to give you one. Mr. Woosley. Anybody else? Anybody else? So I mentioned last class, in case you missed it, you are allowed a formula sheet for the next test. I would advise this being part of it. When I say formula sheet, I mean like this kind of paper. You can write front and back. I don't care what you write on it. You know, like I said, poetry, psalms, proverbs, whatever floats your boat. Examples from differential equations, also fine. Anyway, so we're talking about Laplace transforms. And so the basic strategy is what? Here's the big idea is basically this. Number one, you're given a initial value problem in little y and time t, right? Then what do? You take the Laplace transform of that. And then that gives you an algebraic equation, usually an algebraic equation in big Y and S, all right? Then what you do, algebra, all right? Algebra gets you to Y equals 2 stuff, all right? That's pretty straightforward, usually. Again, there are pathological examples where you actually get a differential equation in Y. So this is not universal advice, but for the ones we'll be looking at, by and large, after we take the Laplace transform, we get an algebraic equation. So you get Y equals stuff. And then the trouble is this stuff may or may not be actually on that table you have, right? So then the next thing you do is partial fractions. And partial fractions basically gives you Y equals nice stuff. All right, nice stuff is stuff that you can take the inverse Laplace transform of, and that gets us back to Y equals 2 answer. This is the thought process. We need to take Laplace transforms, do algebra, do partial fractions to make the stuff look nice, and then we can take inverse Laplace transform, and that's the answer. That is the path through the wilderness. All right, so I'm going to focus, at least for a minute here, on how to take inverse Laplace transforms of things, okay? So example 1. If f of s is equal to s squared plus 4 over s to the 4th minus, well, let's say 81, find the inverse Laplace transform of f, which we usually use a little f for that. So what are we going to do? We need to do partial fractions. So this one, s to the 4th minus 81, well, that is equal to s squared minus 9 times s squared plus 9. And so the standard thing to do here would be to say, aha, well, that's really s minus 3 times s plus 3 times s squared plus 9. That's the real factorization. And so that tells me I should do this. F of s equal to s squared plus 4 over s to the 4th minus 81 equals to a over s minus 3 plus b over s plus 3 plus cs plus d over s squared plus 9. I got to find this a, b, c, d. This is just like calculus 2 when we do partial fractions, same algebra. Let's see here. So that's s to the s squared plus 4 is a times s plus 3 times s squared plus 9 plus b times s minus 3 times s squared plus 9 plus cs plus d times s plus 3 times s minus 3. So I multiply by the denominator. And there are two easy things to do here, right? We can put in s equals to 3, and we can put in s equals to minus 3. That'll immediately tell us some things, right? So if I set s equals to 3, on the left-hand side, what do I get? 13, yeah. And let's see here. This is gone, and that is gone, because when I plug in 3, I get 0 from those terms, right? So the first one gives me a times what? It looks like a 6 times a 18, right? Is it 108? Yeah, it's 108. So therefore, a equals to 13 over 108. There you go. 1 down, 3 to go. S equals minus 3 will also be nice. That's going to give us 13 equals to, let's see here. The first thing is 0. The last thing is 0. The middle term is interesting. That's b times minus 6 times 18. So apparently, b is minus 13 over 108. All right? Now what should I do? Well, in calculus 2, we would have equated coefficients or something here. But for kicks, I think what I'm going to do is I'm going to put s equal to 3i and see what happens. If I put s equals to 3i, what's s squared plus 4? It's minus 1 plus 4, which is 3, right? But what's the deal with 3i? It kills s squared plus 9, right? So it just leaves me this term right here, right? So I get 3 equals to, what is that? 3ci plus d times, what's this going to work out to? Well, I mean, I should rewrite this. Let's not be dumb. This is s squared minus 9, right? This is s squared minus 9. Don't forget your roots. See here, that's minus 10. Yes?
I noticed that we're plugging in 3i into s squared on the left-hand side of the equation. Isn't that negative 9?
Oh, thank you. Right. It was not I, it was 3i. Thank you. Minus 9. So that's not a 3, that's a what? Yeah, negative 5. Okay, thank you. That's better. I very much appreciate that comment. Details do matter. Let's see here, minus 5. And so this gives me a minus 30, 30ic minus 10d. Do we agree? Why is this so much better than plugging in a real value? This is a complex equation. complex equations are two real equations. This is all I need. This immediately tells me from the real part of the above equation that minus 5 is equal to minus 10d, and it tells me from the imaginary part that 0 is equal to minus 30c. So therefore, d is equal to 1/2, and c is equal to 0. And that is a way better way of doing it than I teach Calc 2 students, because they are afeared of the complex numbers. Yes?
And reasons why you don't just multiply it all out and then compare it.
Sure, because this is easier. Yes, you can revert to your Calc 2 ways. I do not, you, fine, if you'd like. This is not the only way. I really don't much care how you do this algebra as long as you can do it. So if you do the homework that will inevitably be assigned with Wolfram Alpha, that's great. You'll get the right answers, but then you're kind of up a creek when you get to the test, right? So you need to work these things out, otherwise you'll be in trouble. Yeah.
So, in doing that, are you like, do you have to assume that C and D are going to be complex?
Yes, that is assumed that A, B, C, and D are real constants.
So do you actually, like, do you know that?
I do know that because there's a theorem which says that there exists a partial fractions decomposition of this rational function in S, and it has this form. To prove that is a problem of abstract algebra, actually Math 422. And in fact, partial fractions exist in some generality over the real number system. You can do it for rings, which maybe we haven't thought about. Anyway, I wouldn't know this except my brother wrote a paper with some students on it. A, what was A? Something awful, 13 over 108 times S minus 3. So, you know, we're about to enter the world of all of the questions I've been asked in Calculus 2. Why is this the partial fractions decomposition? But why? Because I said so is actually the answer I'm going to give you. And it's the same answer I give to Calculus 2, pretty much. But the deeper answer is because it works. Another answer is it's just reverse common denominatoring, if that's a word. But what's my D? Oh, that's 1 over S squared plus 9. Did I mess it up? Where's this 18 you're talking about? Oh man. Same stupid mistake, huh? So that's supposed to be a, oh, you're like, this goes to minus 18. Oh, blast. Oh man. Oh. All right. Minus 54 CI minus 18D. So apparently minus 5 is equal to minus 18D. Should have been suspicious of that half. It seemed too pretty. 0 equals to minus 54C. So C is still 0. Yay. And now D, I mean not now, but like it was always this. It was just that we were wrong. D is equal to 5 over 18. I guess if you have a certain view of truth, we just change the value to 5/18, right? By understanding it to be this. Does that seem crazy? It seems crazy to me. It was never a half. That was wrong. Okay, but anyway. So now we have entered the world of nice stuff. That is nice because I can take the inverse Laplace transform of what's in green at the top of the board with a minimum of effort by just reading the table backwards. So I get 13 over 108. This gives me an e to the 3t. Minus 13 over 108. This gives me an e to the minus 3t. And this guy is 5/18. And that's actually going to be 5/3. No, wait a minute. Yeah, 5/18. I'm sorry, I can't do math. Times 1/6. Still bad. 1/3 sine of 3t. Where'd that third? Why is there a third there? Remember what we worked out last class? We worked out that the Laplace transform of the sine of, say, beta t, right, is beta over s squared plus beta squared, right? So in order to, take inverse Laplace transform of beta over s squared plus beta squared of t to give me sine beta t, I need there to be a beta upstairs, right? So to make that happen, you'd multiply and divide by 3. I think about putting a 3 here. If I do that, then I have to multiply by a third out here, right? So that's where the third comes from. Got to think about that. Does that make sense? Additional fun. This is equal to, let's see here. What's divide by 2? What you got? 13 over what? 54? And this is actually hyperbolic cosine of 3t. Yeah. 5 over, that's a 54, isn't it? 54 sine of 3t. Interesting. Fun fact. The Laplace transform of e to the, say, alpha t, cosh beta t, and the Laplace transform of e to the alpha t, sinh beta t, guess what these are? This actually works out to s minus alpha divided by s minus alpha squared. And it's a hyperbolic cosine instead of a cosine. You know what changes? The sign. That's it. Minus beta squared. Otherwise, same formula as cosine. And the Laplace transform of this is actually beta over, s minus alpha squared minus beta squared. So if you're willing and you want to go down this path, it's sometimes nice to think about these. It would have actually been convenient to use these for this problem because we could have thought about cosh and sinh as opposed to, exponentials. Now, is that better or is it worse? I don't know. You pick your poison, but here's another path that you can go down. See, I could have looked for a partial fractions decomposition. I could have traded this out. I could have replaced that with something like a plus bs. This would be, say, a different a and different b, a bar, b bar, over s squared minus 9. If I'd gone down that path, then I could have looked for cosh and sinh, cosh of 3t and sinh of 3t in the inverse transform. It so happens that a bar is 0 and b bar happens to be 13 over 54, looking at it, yeah.
So the Laplace inverse of f of x is the first.
It's either these are equal, these are the same function. This is written in exponential notation, that's written in hyperbolic cosine notation. Same answer. Yep.
Well, does the red not include the 5/8, 1/3 sine 3t?
Right. I'm just talking about the first two terms. This is it's sines and cosines. It can't be escaped. Here, let's work a couple of simpler examples, which will, I always do this. I give you some sort of awful fourth order example, and then I will pull back and do second order examples. So let's do some second order examples. Probably shouldn't have erased that. Oh well. What's done is done. If I'd been smarter, I would have started with these. But, All right, so f of s equals to 3s plus 7 divided by s squared plus 6s plus, let's say, 13. Find the inverse Laplace transform. Now this one, partial fractions, not your friend, not necessary. Here we just have to do algebra. Straight algebra. So complete the square in the denominator. What's that give us? We have s plus 3 quantity squared, right? Because that will group all the s dependents into one thing, which is squared. If I do that, that's like adding 9, right? But we have a 13 there before. So we have to have plus 4, right? Now, the ultimate judge of whether or not you did the completing the square correctly, all you got to do is take what you just did and multiply it out. When you multiply this out, I'll do it. Look, s plus 3 squared plus 4, what's this? S squared plus 6s plus 9 plus 4, which is equal to s squared plus 6s plus 13. That's what I started with, right? So I'm not changing the expression. I am merely reformulating it, right? These are equal. Why do I do that? I do that so that we're in the world of nice stuff. Almost nice stuff. See, I have one more step. You got to use your imagination. That's obviously 3 times s plus 3. Am I right? And over here, I've got 7 what? That is not true, of course. I mean, I just added 9 to the numerator, haven't I? So to be fair, right, we have no concept of some sort of mathematical debt we can arbitrarily borrow from, from our grandchildren and so forth. So it's up to us now. We have to subtract the 9. We can't put it off. It's got to happen now. Sorry, that's just the way it works. None of you are government majors, so my comments are wasted. I once had a pre-law in calculus, once upon a time. All right, so yeah, that's almost done. Ah, cool, something almost magical has happened. This is an accident. In fact, it's unfortunate that this has happened because it doesn't really help me illustrate the full calculation because we got lucky in that we have 2 upstairs here with a net minus outside. Now, why is that nice? Because for that term, I need the square root of the thing which is added. So like that's a 2 squared in the denominator. I need a 2 upstairs for the inverse transform of the sign to work. Right? If that 2 wasn't there, I'd have to invent it like I did by dividing and multiplying by a third in the previous example. But here it just happened to be that. So great. Here we go. Inverse Laplace transform. This is 3 e to the minus 3t cosine of 2t. This is minus e to the minus 3t sine 2t. So there you go. That's the inverse Laplace transform. Any questions? All right. Let us do another. I would like to erase this, but I will save this and work around it awkwardly. Here's what we're going to do. Dividing line. Aha, there we go. So here's an example 3. Let's look at, let's say, g of s equal to, I don't know, 6s plus 8 divided by s squared plus 4s plus 3. Right. And so this factors, right? This is s plus 3 times s plus 2, right? S plus 1. Yes?
Sorry, going further, in the previous problem, how did you, like, what, from the sheet, which one is that?
That is, what we're doing is we're looking at table 7.1. The last two, we're just going backwards. So it's for the 3, it pulls out, right? The 3 is outside. It's linear. We can pull the 3 out. And so we're just focusing on this piece here. And there, I'm looking at a being minus 3 and b being 2. And that's actually, so for both of them, it's the same song and dance. See, because s plus 3 we look at as s minus a minus 3, right? Because the formulas are for s minus a. You know, does that make sense? So it's the end of table 7.1, which we derived through complex magic last time. Let's see here. So this one, again, the instructions for the problem are find the inverse Laplace transform. That's what we're doing right now. Find the inverse Laplace transform of G. So let's see here. It looks like I should do A over S plus 3 plus B over S plus 1, right? So let's see here. Let's work it out. I'll do it here. So that gives me 6s plus 8 equals a times s plus 1 plus b times s plus 3. What is it? Oh, now I use this. I used it last time. What are you talking about? Now I use this. All right. I'm going to ignore these comments. All right, 2 equals to well, apparently 2b. So to be or not to be? Well, no, I mean b is 1. Let's see here. B is 1. S equals to minus 3 gives me minus 18 plus 8, which is minus 10. And minus 10 is equal to minus 3 plus 1, which is minus 2a. Apparently, a is equal to 5. Not to be confused with s. And if you'll allow me to erase that so that it doesn't clutter things here. So what we found is that this is actually equal to, tell you what, I'll do it down here. So therefore, g of s is what? G of s is equal to 5 over s plus 3 plus 1 over s plus 1. This is nice. The reason this is nice is because we can go to table 7 point, whatever it was, 7.1, and this is like the second one down the list, right? These are just plain old garden variety exponentials. And so take the inverse Laplace transform of this guy. And we get g of t is equal to 5 e to the minus 3t plus e to the minus t. So if you see how to factor this, great, right? But there's another way you can do this, which I would be remiss if I didn't show you. I'm not sure this is a good way for many of you to do it, but it's a way that you can do it. The other way to do it is just always to complete the square. So if I go down this other path, a hulkish path, let's see here, a plus s plus 2 squared, then I have to do what? Minus 1, right? So you got to use your imagination a little bit. That's 6 times s plus 2. I just added 12, so I have to subtract 12. That gives me a net of minus 4. And then inverse Laplace transform, and I get g of t is 6 e to the minus 2t cosh t minus 4 e to the minus 2t sinh t. Now you might think the blue answer is better. I probably would agree with you, but that is the correct answer. If you multiply it out, you can see that they're the same thing. That's probably good for us to do. This is 6 e to the minus 2t, 1/2 e to the t plus e to the minus t, right? Minus 4 e to the minus 2t times 1/2 e to the t minus e to the minus t. Multiply that out. You've got this times this is an e to the minus t. I got 3 of them from here. This times this is an e to the minus t. I've got minus 2 of them from here. Oh, man. I said something wrong. Three minus 2 is what? Is 1, which is what I want, right? E to the minus t, there's 1 of them. Duh. So collect the e to the minus t, you got 3 of them here, you got minus 1 of them over there, so you get 1. The e to the minus 3t terms, you get 3 from this, and then you get 2 from this. 3 plus 2 is 5. Same answer. So if you want a kind of boring way to do quadratic problems, you can always complete the square. And you either get sines and cosines, or you get coshes and sinh. And if when you complete the square, it's a perfect square, what happens then? What if I have, h of s equals to 3s plus 2 over s squared plus 6s plus 9? I complete the square on the denominator. What happens? It's like, but yeah, it's completed. So there's no adding because it was already a perfect square. This is the middle ground. This is between cosine and sine and cosh and sinh. And then you just got to use your imagination like usual. That's 3 times s plus 3 minus what? Minus a 9, so that's minus 7 because there was a 2 there to start with. Then you do algebra. And then you go to the table. These are the 3 possible cases for a quadratic denominator with a linear numerator. And it corresponds to the 3 possible cases that we get for the constant coefficient problem. Right? If you're looking at ay prime plus by prime plus cy equals to 0, the solutions are either exponentials, sines and cosines times exponentials, or what comes of this? What comes of this? The inverse Laplace transform of h is what? That piece is a 3 e to the minus 3t, and this is a minus 7t e to the minus 3t. This is not good. What do you mean? Them's fighting words. Oh, it's something on the phone. Was it? What happened? Is something interesting happening? What's that? Oh, grades. Ah, grades. Yes, grades. What was graded? The second exam and what? What was it? This is exciting. I'm glad I could be here to share this with you all. What is this? Who graded what? I still remember when I was an undergraduate going to visit a professor in the physics building. There's this graduate student. I did not know her, sitting on the floor, and she looked up at me and she goes, "Dr. Blondin doesn't know it, but he just had a near-death experience." I still remember that to this day. I never had any classes with Dr. Blondin. He was one of these guys who builds stars on computers, you know. And so his thing to do would be to work on making hurricanes logos appear in his various scientific publications. So the Hurricanes were the local, I think, hockey team in Raleigh. I forget. I mean, I think that's right. Is that right? Hurricanes is hockey team in Raleigh. Do you guys, anybody know? No big hockey fans? Okay. So, yeah. His plots of, like, stellar whatever, if there was, like, a swirl, and they would always be colored with the team colors, and it was rather obvious what was going on. Oh, you guys got this? Can I erase? All right. So, of course, you know, there are more cases. It's partial fractions. All of the cases that you saw in Calculus 2 appear here again, pretty much. I will give you some homework. You will experience the rest of it, but I've showed you most of the big ideas here. Yeah.
I was looking at the board when you're doing those hydraulic cosines and hydraulic sines. You're doing that mostly when you have, for hydraulic cosine, it's s over s squared minus b squared.
Right.
And for hydraulic sine, it's b over s squared minus b squared.
Yeah, both. So when we complete the square, what's going to happen is either we're going to get something squared minus a constant squared, or we're going to get something squared plus a constant squared. When it's minus a constant squared, that reveals the fact that that quadratic actually has real roots. It can be factored. If you look at the graph of it, it crosses the x-axis in two distinct places. If when you complete the square, this happens, if you just thought about graphing the quadratic like x plus 3 squared, it bounces. It just goes to x equals minus 3 and bounces off the x-axis. So there's these three cases with quadratics. Either we have no real zeros, you know, which means that it like opens up and never crosses the x-axis, or we have distinct real zeros. See, this, if you think about it, it means we can factor. So what is that? Well, that's s minus alpha parentheses minus beta times s minus alpha parentheses plus beta. See, this is the difference of perfect squares, which means you can factor it like this. For the one we were looking at, s squared minus 3s, plus, what was it? S squared plus 4s plus 3, was it? So we were like s plus 2 squared minus 1, right? So that is s plus 2 plus, well, minus 1 times s plus 2 plus 1, right? Which is what I wrote originally, which was s plus 1 times s plus 3. So, you know, it all goes back to the study of quadratics. You know, there's these three cases when we're factoring them. And they give us different kinds of behavior as we study differential equations. All right, that said, I must turn the page here and go on to the next bit, which is discontinuous things. Discontinuous fun. There we go. So the first thing we need is a tool to look at things. So I'll show you an example. First, I should make a definition. The gate function from a to b of t. What this is going to be is it is going to be 0 for t less than a. It's going to be 1 for a less than t less than b. And it's going to be 0 for t greater than b. And I just don't feel like defining it at the jumps, so whatever. You can make it whatever you want at the jumps. I don't care. It's up to you, whatever. And the cool thing is you can build this from unit step functions. This is the unit step function of t minus b minus the unit step function of t minus a. Let me plot things here. So the unit step function, this one, what this looks like if we graph it, is it turns on at time b. And it's just 1 from that point on, right? This is, so it's 0 before that, and it's 1 after b. In contrast, the unit step function of t minus a, it turns on at time a like that, right? I'm going to assume that a is less than b, all right? So what happens when you take the difference? Oh, you see already that I made my formula wrong, right? My formula's wrong. Because I've drawn these graphs, I'm committed to doing this. But what I should have written was this. This is a gate function. It's just 1 from time a to time b, and elsewhere it's 0. Does that make sense? I mean, this is a formula for it. We can look at it as the difference of unit step functions. All right? So again, the graph of what we're interested in, it's just like a pulse. It's 1 here. It's 0 elsewhere. Let me graph the graph in black so you can see the difference, or green. There we go. Right, this is the graph of g of a comma b. We'll also sometimes need like g of a comma infinity. What would that mean? That would be like we turn it on at time a and we just leave it on. Like my children with the lights around the house. They never turn them off. This is their gate function for that. So this would just be u of t minus a. That turns on at time a, and it just never turns off. All right? So gate functions make it really easy to write formulas for case-wise defined functions. Let me show you. So let's apply these. To make nice formulas for case-wise defined functions. Case-wise defined functions, the bane of Calculus 1 students' existence. Like I did something with case-wise defined functions. I covered Dr. Smith's class the other day, and like, you know, when I started talking about the absolute value function and the fact that it had different formulas in different places, you'd think that I had like transformed into a dragon or something the way they were looking at me. It was like, what are you doing? There's different formulas in different places. It's like, not good. Not good. I don't know what's happening with the input from high school, but it's not good. Anyway, case-wise defined function. So here it is. If we have f of t, let's say it's t for 0 less than t less than 3, and then it's say sine of t for 3 less than t less than 7, and then let's say it's t squared for t greater than 7. Well, this is a case-wise defined function, right? 3 cases. And here's the formula for it in terms of gate functions. This is t times the gate function from 0 to 3 plus the sine of t times the gate function from 3 to 7, and then plus t squared times the gate function from 7 to infinity. It's like too easy, right? So just you switch the function, you switch the case on when the case happens, and the gate function automatically makes it go to 0 outside that range of t. Stupidly simple. But it turns out we need to rewrite this in terms of unit step functions to actually take Laplace transforms. All right? So what does this look like in terms of Laplace transforms? What does this look like in terms of step functions? Well, this is t, right, times u of t minus u of t minus 3, parentheses, plus the sine of t times u of t minus 3 minus u of t minus 7, plus t squared times u of t minus 7. And then it turns out when we actually take Laplace transforms, we're going to want to group things. So we've got like this t u of t at the start. That's there. And then we've got things with u t minus 3. So we've got a sine t, and we've got a minus t. I like to put the minus second, because, I don't know, it just seems right to write it like that. I hate writing the minus thing first, And then I've got my other terms, t squared minus the sine of t, u of t minus 7. Now, if I was more invested in confusing the students, I would just go straight from here to here and never explain it. And then you guys would be like, what? Right? But I try to introduce these gate functions so that you can see why I'm doing that, where the formula comes from that I just underline in red. Are we good? All right, so Laplace transforms. What happens when we take the Laplace transform of a unit step function times a Laplace transformable function? So we need to work something out. The question is, what is the Laplace transform of f of t times u of t minus a? So go back to the definition from last time. Integral from 0 to infinity. E to the minus st. F of t, u of t minus a, dt. So you guys tell me, what's the first thing I can do calculationally here? Do I need to integrate from 0? This function, f of t times u of t minus a, what's that look like from, remember u of t minus a is this thing, right? So when you take that thing, which is 0, right? It's 0 over here. I'm taking 0 times a function. This integral is 0. We're integrating the 0 function all the way up till time a, right? So I can change the lower bound to a, and it doesn't lose anything. Oh, and I don't even need the u of t minus a after that point, do I? Because over here, it's equal to 1, right? for t greater than a. Everybody follow? Now, at this point, it's not a Laplace transform, right? Because the lower bound is from a, it's not from 0. To make this into a Laplace transform, I need to make a change of variables that changes that a to 0. So I should let's say u equal to maybe, I don't know, how about t minus a, right? So then when t is equal to a, that will imply that u is equal to 0, right? So we make that substitution, and that will change the bounds to ones that at least make contact with the Laplace transform, 0 to infinity. And then I've got e to the minus s times t, but what's t? T is equal to u plus a, right? So minus s times u plus a, and then f of what? T, which is what? U plus a. And then what's my dt? du, right? Now, we just need to do a little bit of math here. This is the integral from 0 to infinity of, well, that's e to the minus as, e to the minus su, f of u plus a du. So let me just, if you don't mind, go ahead and make the decision to pull that e to the minus as out front of the integral. We can do that because it has no what? No, it's got no u dependence. S is a fixed but arbitrary transform variable from the outset of this, right? S is a free variable. It's got nothing to do with the integration. I can pull e to the minus as out. And then we got this. What's that? Think of, now we can, if you want, I can change the u back to a t so you can see it more clearly, but this is the Laplace transform of what? What function? F of t plus a of s. If it helps you, I can write one more step. This is e to the minus as, the integral from 0 to infinity, change the variable back to t. It is just a dummy variable of integration, so we can change it from u to t if we want. If it bothered you, oh, wait a minute, no, we haven't gotten to that. Never mind. So this is the Laplace transform of that. Oh, there's your formula. So therefore, the Laplace transform of f of t times u of t minus a, right, of s is equal to e to the minus as times the Laplace transform of f of t plus a of s. So this is how we take the Laplace transform of a function times a exponential. Excuse me, a function times a unit step function. I can't talk today. Now, it's often, this is not super convenient for the, it's useful to think about what would happen if we let f of t equal to g of t minus a. Suppose we do that. Suppose we invent a new function g and say g of t minus a is f of t. We can still do this whole derivation. What would it tell us? It would tell us that the Laplace transform of g of t minus a is what? T minus a times u of t minus a, what would it be equal to? E to the minus as, the Laplace transform of g of t minus a plus a, right? Which is just what? g of t, right? And so that gives us our beloved formula, which is that the inverse Laplace transform of e to the minus as times big G of s at time t, well, that is nothing more than g of t minus a times u of t minus a. This is often, these two formulas are pretty much, these are the mission critical formulas for calculating. So like, let me just connect these to our larger thought pattern. This formula, let me call this star, let me call this star star. So star, here we'd use star. All right? Here we'd use star star. So both are important formulas to know and to be able to implement at these different stages in the calculation. So I'm not actually going to do it because it would be awful and take 20 minutes. But we have everything we need to take the Laplace transform of this now, right? Because this is nothing more than functions times unit step functions, right? And so to do that, I just take e to the minus whatever times the Laplace transform of the shifted function, all right? So rather than making the mistake that I sometimes make of trying to actually work the Laplace transform of this out, I will dial it back and do it on a simple sub-piece of this, all right? You're like, would you give us some homework just like this, though? Like, oh, yeah, of course. I mean, ask me. I could do that. You guys have no projects due, and so, you know, it's not that part of the semester when you have projects due, so that's good. So here. Let's see here. Example, let's see here. What example? Sorry, example. What? Oh, 6? Thank you. Mucho appreciated. All right, so let's consider f of t equals to, I don't know. Let's make it be sine t and then 3, and this will be 0 less than t less than 2. And I'll make it simpler. Let me make it pi over 2. That's nicer. That's nicer. And t greater than pi over 2. All right. Yes?
I'm a little confused if I'm reading the sheet correctly. It seems like the formula they have is different than the one you have over here.
Uh-oh. That is disturbing.
For the top one. They have, at the beginning, they have t minus a.
Well, notice the sheet, I have a g. Like equation 8, there's a g. The role of f and g may be reversed, yeah?
Are we not at equation 5?
You want to talk about equation 5?
That's not what that is.
Equation 5 is this, is star star, but it's with the L on the other side. Listen, the thing that might be confusing you is the role of f and g are reversed in the formulas on the sheet. Here, f and g are arbitrary functions I'm trying to communicate a pattern with. It's unfortunate, but true, that the f and the g which appear in the sheet are playing mirrored roles to what's on the